We will continue with discrete time Markov chain. In the last class, we discussed about the eigenvalue analysis of the matrix P. So, P matrix, we consider the P matrix, that is the state transition probability matrix, TPM, state transition probability matrix. Now, this matrix has a special property that row sum is equal to 1, but in terms of the eigenvalues, we observe that lambda 1 eigenvalue is always 1, rest of the eigenvalues have magnitude less than equal to 1 for I is equal to 2, 3 etc. up to n. So, that way this stochastic matrix has special properties in terms of the eigenvalues, and that we exploited to find out the that is steady state probability pi I is equal to 0, 1 up to n minus 1. So, these steady state probabilities can be obtained by using the eigenvalue analysis. But for a general matrix, when this state matrix, state transition probability matrix is very large, this type of analysis is not easy. Therefore, in this lecture we will try to exploit the structure of this chain in terms of this matrix, so that we can classify the states and discuss their properties. So, classification of states. This classification helped in determining the steady state probabilities of the states. So, that way this classification is important. Now, we will start with communication relation. A state J is said to be accessible from state I if the chain can reach state J at some instant of time starting from state I. Thus, what does it mean? That this state J is accessible from state I, That means there is a finite probability Pijn is greater than 0 for some n greater than equal to 0. So, you can reach state J from state I with certain probability at certain instant. This property is denoted by I is connected to J. And now, similarly, if J can be also connected to I, so that way we define the communication relationship. The states I and J are said to communicate with each other if I can access J and J can access I. So, we write this notation that I communicate with J, this notation is used. Thus, I communicate with J if I can access J and J can access I, or we can write in terms of some probability. Suppose that means there exists some m n greater than equal to 0 such that I j m is greater than equal to greater than 0 and p j I n. So, at this instant this probability is greater than 0, then only we say that I and j communicates. Communication is an important property. We will give an example to illustrate the communication relation. Consider a 4-state Markov chain. Suppose 0, 1, 2 and 3, these are the states. Now, 0 can access 1, 2 can access 3, 3 can access 2 and 3 can access 0. Now, we see that state 2 is not accessible from state 0. State 2 and 3 they communicate because there is a two-way path between them. Communication is an equivalence relation in the sense that it is reflective, that is I communicate with I itself, that is from definition. Symmetric I communicate with J implies that J communicate with I. This is again from the definition, and it is transitive. Communication is a transitive operation if J is is communicating with I and it is communicating with K. Suppose I also, J is communicating with I also, J is communicating with K also, then I and K will communicate. This can be also easily proved. So, this way this communication relationship can be exploited to study the property of the Markov chain. Now, the relation communication defines a distinct subset of the state space V of an MC, that is a Markov chain, called the communicating classes. Now, we will consider a special collection of subsets of V such that each member of C communicate with each other. A communicating class C is a subset of V such that each state in C communicates with one another. So, that is the definition of communicating class. A communicating class C is called closed. Now, another important property, that closed. A communicating class C is called closed if for any J belonging to C complement, that is not in C, is not accessible from I component I belonging to C. So, this is what does it mean? Suppose I have a communicating class, this is a communicating class. Now, any member, suppose J is not, it is a state not in this communicating class, then it cannot be accessed from any member in this communicating class I. So, there is no path between I and J. Okay. So, a communicating class C is called closed if any J belonging to C complement is not accessible from I belonging to C. This J is not accessible from this communicating class, therefore, C is closed. So, in terms of transition probability, we can say that for all I belonging to C and for J belonging to C complement, Pij is equal to 0. It means that for the communicating class C, if I consider any state I, then this probability Ij, J belonging to C, that must be equal to 1, because from state I there may be transition to members of C only, it cannot go out. Therefore, this probability, sum of these probabilities must be equal to 1. And the matrix, now we can define a new matrix P1, that is Pij, Ij belonging to C. This will also be a stochastic matrix. So, this subchain defined by this closed class C will be a Markov chain with a transition matrix P1. So, that is one important observation. So, that way we discussed about closed communicating classes. So, communicating class, each member each state communicate with each other, and closed means there is no path between that class and its complement. So, we defined communicating class, we can give an example. Suppose this is again a 4 state chain. Now, here states are 0, 1, 2, 3. We see that this is 0, 1 and 1 to 0, this is a communicating class, 2 to 3, then again 2, that is a communicating class. We see that C1 is not closed. Why it is not closed? From C1 there is a path to state 2, which is not a member of this class. But C2 is a closed class. Why? Because it is a communicating class, but there is no path from 2 and 3 to any state in the chain. So, that way in this example C1 is not closed, but C2 is closed. So, we defined closed communicating class. Now, we can define irreducible chain. This state transition matrix P is called irreducible if V is a communicating class and there is no other communicating class in V. What does it mean? The state transition matrix P is called irreducible if its state space V is a communicating class. Entire states will form a communicating class, and there is no other communicating class in V. So, that way in that case the stochastic matrix P will be called irreducible, and the corresponding Markov chain is called irreducible. So, that way for an irreducible Markov chain the matrix P is irreducible. What does it mean? That there is all states form a communicating class and there is no other communicating class in V. So, that way we have defined irreducible Markov chain. A Markov chain can be irreducible, means all its states communicate with each other and there is no other communicating class. Only entire state space form a communicating class and there is no other communicating class. Now, when we discussed about closed class C, we may have a very special case of communicating class, closed communicating class which has only one member. So, if a closed class C consists of only one state I, closed class means closed communicating class. Closed communicating class C consists of, if it consists of only one state I, then I is called an absorbing state. Thus, the state I with P I equal to 1 is an absorbing state. So, we have again define another term, that is absorbing state. What is an absorbing state? So, once the chain come to this state, it will remain at that state with probability 1. So, that way we define the irreducible Markov chain, also what is an absorbing state. We will consider one example. This is a classical problem known as gambler's ruin problem. A man starts to gamble with 2 units of money which he wants to double. Each time he wins a game, he gets 1 unit, and if he loses, he loses 1 unit. The probability of the gambler winning a particular game is P, and the play stops if the gambler wins 2 units. That means he wants to double. When he has 4 units, he will stop, or he loses all 2 units. So, we want to identify the communicating classes here. So, we see that this is a Markov chain and it has state 0, 1, 2, 3, 4. Actually, this action is the Markov chain that represents the total fortune of the gambler after nth game. So, after nth game, what is his fortune? So, after nth game, his fortune may be 0, he lost all his money, 1, 2, 3 or 4, that is he has doubled the money. So, that way if I write the transition probability matrix, so that way if it is a state 0, it is state 0 suppose, then it will remain at state 0, that is with probability 1, rest is 0. Similarly, when it is in state 1, it can go to state 0 with 1 minus p and to state 2 with probability p. State p is the state transition matrix for this gambler's ruin problem. Xn is the Markov chain that represents the total fortune of the gambler after nth game, and state space is 0, 1, 2, 3, 4. P is given by this. Now, if gambler has 0 money, then he will remain at 0 only, the game will stop. So, that way when for state 0, P 0 0 is equal to 1. Similarly, if gambler has 1 unit, so from 1 you can go to 0 with probability 1 minus p, or if he wins, he will go to state 2 with probability p. Similarly, for state 2, he can go to state 1 and state 3. For state 3, he can go to state 2 and state 4, and finally if he arrive at state 1, that there is no return, he has to remain there. So state 4 is an absorbing state. So if it is there, it will remain there with probability 1. So that way we see that this is the transition probability matrix for the Gambler-Lewin problem. We can represent in graphical form. Suppose it is in state 0, then it will remain in state 0 with probability 1. This is probability 1. Now, when it is in state 1, it can go to state 2 with probability p, and it can come back to state 0 with probability 1 minus p. Similarly, when it is in state 2, it can go to state 3 with probability p and come back to state 1 with probability 1 minus p. And like that, when it is in state 3, it can come back to state 2 with probability 1 minus p and go to state 4 with probability p. Finally, if it is in state 4, it will remain in state 4 with probability 1. So that way we can see that 0 is a communicating class, 4 is a communicating class with single state, and 1, 2, 3 is also communicating class. 1, 2, 3, 1, 2, 3, because there is a path from 1 to 2, you can go 2 to 3, then 3 to 2, 2 to 1. So that way it is a communicating class, and out of this, if once it is in state 4, it cannot come back to any other state. So 4 is a closed class. Similarly, 0 is a closed class, and 0, but 1 to 3 is not closed. So this is not closed. And we also notice that 0 and 4 are the absorbing states. Next, we will define periodic and aperiodic Markov chains. A state I is said to be periodic with a period d if pi I n is equal to 0, unless n is a multiple of d and d is the greatest integer with this property. So what does it mean? That this pi I n will be equal to 0 unless it is a n is a multiple of d. So it will be non-zero at integer multiples of d. So what does it mean? Again, a path leading back to a state I has length in multiple of d. This is a important thing, that it is a periodic with period d, means that a path leading back to a state I from I to I, suppose from 0 to 0 you want to come back, then a path will have length in multiple of d. Thus, in the following graph, each state is periodic with a period 2, because state 0 we can come back, we can go here and then come back. So that is we can come back at 2 steps, or we can go 0 to 1, 1 to 2, then 2 to 1 and again 1 to 0. So that way we can come back to 0 in step 4 also. Like that we can come back to 0 in number of steps in multiple of 2. So that way this d is the greatest common divisor of n such that pi I n is greater than equal to 0. If d is 1, then this chain is called aperiodic. So that way we have defined periodic Markov chain, where each state will be visited periodically, and if it is not periodic, it is called an aperiodic Markov chain. With this background, we will define what is known as the recurrence property of states. Recurrence means, suppose if a state is visited again and again. For this study, we need certain terms. First, we will define first passage probability, that is Fij n. What does it mean? That it visits state j for the first time, given that initially at state I. So, therefore, this is the probability that xn is equal to j, x1 not equal to j, x2 not equal to j, like that xn n minus 1 not equal to j. Given that x0 is equal to 1, for the first time xn will become j. So, this probability is called first passage probability from state I to state j. For the first time there will be a passage. What is the probability? Similarly, we can define the first return probability at step n. Suppose what does it mean? Probability that xn is equal to I and x1 is not equal to I, for x2 not equal to I, like that xn minus 1 is not equal to I, given that x0 is equal to I. So, given that x0 is equal to I, for the first time xn will become I. So, that probability is known as the first return probability. Starting with state I, at nth step we will get state I for the first time. Now, we can define now this quantity Fij, that is the probability that this chain will eventually pass through state j, given that it is at state I at n is equal to 0. So, this is the probability. Fij is the probability that this chain will eventually pass through state j, given that it is at I at n is equal to 0. So, this is the probability we have defined. We use this symbol Fij, suppose Ij and Fi comma j. This is for brevity we use this, but essentially we should have written like this. So, normally we will use these two symbols, that is suffix ij and suffix I comma j and suffix ij, we will be using interchangeably. Now, how we can get Fij, that is equal to probability that xn is equal to j, given that x0 is equal to I and remaining states are at remaining instant of time, this state is not equal to j. So, that way we can consider this probability. Suppose this may happen that for the first time xn will be equal to j, at n is equal to 1, it may happen at n is equal to 2, etc. So, that way it will be the summation of Fij n, where n goes from 1 to infinity. So, this is the probability that starting with state I at n is equal to 0, the chain will pass through j at some time. Eventually, it will pass through state j, given that it is in state I at n is equal to 0, and this is given by the sum of the first passage probabilities. Similarly, Fii, this is the probability that this chain will return to state I, given that it is at state I at n is equal to 0. What is Fii? This is the probability that the MC will return to state I eventually, given that it is at state I at n is equal to 0. So, that way it will be also sum of the first return probabilities Fii n going from 1 to infinity. Now, this sum Fii or Fii, it may be 1 or it may be less than 1. If it is, suppose this quantity is 1, what does it mean? The probability that the chain will eventually return to state I, given that it is at state I at n is equal to 0, this probability is equal to 1. That means, this chain will certainly visit the state I. And similarly, from state, if this quantity is equal to 1, then this chain will pass through state j at some time with probability 1, given that at n is equal to 0 it is at state I. So, that way this probability may be 1 or less than 1. So, on the basis of that, now we can define the transient and recurrent state as Fii may not be equal to 1. So, there is a, if it is not equal to 1, then 1 minus Fii, that will be the probability that chain will not return to state I. Based on this, a state I is called transient if Fii is less than 1. In that case, there is a probability that chain will not return to state I. Otherwise, the chain is called a recurrent state. So, in the case of a recurrent state, Fii is equal to 1. So, starting at state I, there is a probability that eventually it will return to state I. That probability is equal to 1. Let us consider one example. This is a 4-state Markov chain. States are 0, 1, 2 up to 3. Now, considering state 0, the first return probability, if I see that this is P0, 0 is equal to 1/3, that means it can come back to state 0 with probability 1/3. So, therefore, F001 is equal to 1/3. Similarly, F002, now it can go to state 1, and from state 1 it can come back to state 0. So, that way F002 is equal to 2/3 into 1. So, probability that it will go to state 1, that is 2/3, and then from 2/3 it will, from state 1 it will come back to state 0, that probability is 1, that is why multiplied by 1. So, that is equal to 2/3. And F003 for any n greater than equal to 2, that will be equal to 0, okay, because there is no other path that it has come back to state 0. So, that way now we can find out F00, that is equal to F001 plus F002, and that is equal to 1/3 plus 2/3, that is equal to 1. So, that way this state will be now a recurrent state. State 0 is recurrent. Let us examine state 3. So, from state 3 it can return to state 3 in step 1 itself. So, that way F331 is equal to half. Now, there is no other path that it will return to state 3. So, that way it can go to suppose state 2, but from state 2 it cannot come back to state 3. So, that way for any other time F332 will be equal to 0, like that. So, F33 n will be equal to 0 for n greater than equal to 2. Therefore, in this case F33 will be equal to that is F331 1 plus F33 2 etc. But all these values are 0, therefore, this will be simply equal to half, which is less than 1. Therefore, state 3 is transient. Let us summarize the lecture. These states I and J are said to communicate with each other, and this is the symbol I communicate with J, if I can access J and J can access I. And what does it mean? There exists some number m and n such that Pij m is greater than 0 and Pji n is greater than 0. That means m step probability from I to j is greater than 0 and n step probability from state j to I is greater than 0. So in that case we say that state I and j communicate. On the basis of communication, we partition the chain into some communicating classes. A communicating class C is a subset of V such that each state in C communicates with one another. A communicating class C is called closed if any j belonging to C complement is not accessible from I belonging to C. Thus C is closed if for all I belonging to C and j belonging to C complement Pij is equal to 0. So there is no transition from I in C and j in C complement. Thus there is no transition from any state I in C to a state j in C complement. A state I is periodic if a path leading back to a state I has length in multiple of d. This d is the period. So therefore state transition probability and step transition probability from state I back to state I is equal to 0 if it is not a n is not a multiple of d. We also defined the probability Fij, that is the probability that this chain will eventually pass through state j, given that it has started at state I at n is equal to 0. So eventually it will pass through state j. So that probability is related to the first passage probability. Fij is the first passage probability. So that is Fij, this probability is the sum of all the first passage probabilities starting with n to infinity. Now what is the first passage probability? That is probability that xn is equal to j, and it is not equal to j for all earlier instances up to n minus 1, given that x0 is equal to I. So this is the for the first time starting with state I, it will cross j at instant n. Similarly, we can define Fii, that is the probability that the chain will eventually return to state I, and this is also given by like this. This will be summation of the first return probabilities. Now on the basis of this quantity Fii, we defined transient and recurrent states. A state I is transient if Fii is less than 1, otherwise it is called a recurrent state. So in the case of recurrent state, Fii is equal to 1. Thank you.